All right, and the last talk of this session will be given by Ramanathan Thinniyam, who will tell us about reachability in continuous pushdown VASS.
Okay, so what does that mean? Can you do it on this side?
Yeah.
Is that okay? Okay, so hi, I'm Ram. This is joint work with Bala, Rupak, Majumdar, and Georg Zetzsche. Most of this was done while I was at Max Planck. Now I'm at Uppsala. Yeah. So maybe I'll just go over the title bit by bit so that you understand what the problem is. Reachability in continuous pushdown VASS. So to begin with, what are pushdown VASS? So before we go to pushdown VASS, maybe I'll just talk about what are VASS, right? These are vector addition systems with states. So you can think of this as a model where you have finitely many counters. So here there's 4 of them. And there's finitely many global states. So here's Q1 through Qn. And there's some finite set of rules which says you can move from some state to some other state while removing tokens from the counters. So here, for example, we moved from this configuration where we were in Q1 with this things in the counters, and then we moved to Q2. So here we applied this rule where we subtracted 1 from the green counter and we added 1 to the blue. So here it's important that the counters are required to stay non-negative always. So for instance, if you had no green tokens at all, then we could not have applied this particular rule. So from a program standpoint, you can think of VASS as modeling regular threads with asynchronous calls, right? So each thread is very simple, it's finite state, but you also have dynamic spawning, so you can spawn, and of course the assumption is that there's some finitely many different states in which you can be. So this means that with a finite number of counters, you can keep track of how many threads are there at any given point of time, right? So it's a very, let's say, central model of computation. So what's pushdown VASS? What you would expect, right? So it's VASS equipped with 1 stack. I think it's well known that if you just have 2 stacks, this is already a model of computation which is Turing complete. But here, so we have 1 stack and you have a lot of these counters which are VASS counters. So with this, you can model programs where you have 1 thread which is also allowed recursive calls. And so this means you can sort of abstractly, you can push or pop on the stack, while at the same time you can add or decrease to and from the counters. So formally, this configuration of a PVASS is a tuple, which is the state Q, and there's a stack content, which is W. And then there's the values of the K counters, some N1 through Nk, which are numbers. Okay, so here is an example. So, so here's a PVASS with 2 counters and stack alphabet AB. You have 4 states, Q0 through Q3, and the edges on the labels on the edges are transitions. So if you look at T1, so this says decrement the first counter by 1, do nothing to the second counter, while pushing an A on the stack. Right? So if you have on some edges, I have an A bar or a B bar, so that stands for a pop, whereas just the A or the B stands for a push. So here, if you have a current configuration which is, let's say, Q0, some W, N1, N2, where N1 is strictly more than 0, then using T1, we can move to the configuration Q1, WA, N1 minus 1, N2. So sometimes we just write the configuration more succinctly as QWV, where we sum vector of counter values. We also define this ordering relation on on vectors, so V and V prime. So we say that V is less than equal to V prime if V prime is at least as large as V in each coordinate. And we extend this notion to configurations. So where the state and the stack content is the same, but the V is smaller than the V prime. So that's just about the model. So the next thing is what is reachability. So this is a very central sort of problem in most models of computation, where you ask, there is some configuration Cn, and is it reachable from a configuration C1? And we say it is if there is some sequence starting from C1, so C1, C2, dot, 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 till Cn, such that for each Ci, you can transition to the next configuration, Ci plus 1. There is also a notion, related notion, which is coverability. This is where our ordering notion comes into play. Right? So it's, you say, similarly you have going from C1 to Cn, you have a sequence of transitions, and then you say that a configuration Cm is coverable from C1 if this final configuration Cn is at least as large as Cm. So often the coverability is used to model things like just reaching some part of the state, right? Like just the global state and the stack, where you're not interested in how many things are in the task buffer, this kind of thing. So usually it's an easier problem than reachability. So let's just quickly see what these things look like in our example. So Q2 comma epsilon, so epsilon is just an empty stack. 0, 3 is reachable from Q0, epsilon 1, 0, right? So first you can go from Q0 to Q1 via T1, and then you go from Q1 to Q2. So that corresponds to these two transitions, right? So you go from Q0 epsilon 1, 0, you decreased this first counter by 1, you pushed A onto the stack, so you get Q1 A 0, 0, and then you can take the next transition where you don't do anything on the counters and you pop this A. So you get to Q2 epsilon 0, 0. Now you can go back from Q2 to Q1 while adding to the second counter and pushing an A. So you go to Q1 A 0, 1. So now you can see that you can sort of go back and forth, and you can, after 2 more cycles around this loop, you will get to Q2 epsilon 0, 3. So note that Q2 epsilon 0, 3 is not reachable from, for example, Q0 epsilon 0, 0, because as I said, you cannot go below 0. So you cannot fire either of these transitions, T1 or T2, right? Because you need something in either of these counters to go to the next thing. So what about coverability? So Q2 epsilon 0, 3 is coverable from Q0 epsilon 2, 2, right? So you can take a similar kind of sequence of transitions where you go from Q0 to Q1, and then Q2, and then Q1, and so finally what you can do is you can reach Q2 epsilon 1, 3, so which is a bigger configuration than Q2 epsilon 0, 3. But note that you cannot reach Q2 epsilon 0, 3 from Q0 epsilon 2, 2, because you will never be able to remove the second initial token which is present in the second counter, right? So there's only this one time that you decrement, right when you go from Q0 to Q1, and then after that you can't take away the remaining token which is still there. So which means that you can't reach it, but you can cover. So I just want to talk a little bit about the fact that these kind of problems, the reachability problem, just for VASS to begin with, is already known to be really difficult. So only very recently it was shown that reachability for vector addition systems with states is Ackermann complete. This means that essentially this Ackermann is a function which grows faster than any fixed tower height of exponentials. So this is a function which grows crazy fast. Even the coverability problem is not very easy. So coverability for VASS is known to be exponential space complete. So obviously the general case of PVASS, it's something which is more, you're adding a stack to a VASS, so it inherits this Ackermann lower bound from VASS. And the decidability of reachability in PVASS remains open despite our best efforts, even for just one counter and one stack. And so in the theory community, this is an object of central concern with lots of people wanting to see what happens. So naturally, there has been a lot of work on approximations, because this is a model which sort of combines sequential computation, that is a stack, with concurrent computation, which is counters. So the track that we will take is that of continuous Pushdown VASS. So what is the continuous approximation? So a continuous PVASS is one in which if you have some transition, then it can be fired fractionally. So here, when I say fractionally, I'm only talking about the counters. I'm not talking about the stack. The stack is always discrete. But if you have like a -1 +1 on two counters, then you can, let's say, fire this by half. So in general, this firing fraction is some rational number, which is in open 0, close 1. And you can choose this independently at each step. So here again, going back to our example. So if you fire T1, this transition T1 with fraction 0.5, then you can reach Q1A 0.51 from Q0 epsilon 1. So this also means that you can cover Q1A half from Q0 epsilon 1. But note that you cannot cover Q1A 1 from Q0 epsilon 1 because of the fact that you can take some very small fraction, but it's going to take something away, right? So that's why it's open 0, close 1. Right, so this has some history, so I'll just briefly mention. Continuous approximations were first introduced by David and Ala back in '87, in fact, for Petri nets. Reachability was shown to be P-complete for Petri nets by Fraka Haddad in 2015. And then in 2017, it was reachability for continuous VASS was shown to be NP-complete. So roughly the difference between Petri net and VASS is the addition of discrete states. And this seems to somehow give you this jump, right, like from P to NP. Despite this, this is a massive reduction in complexity. So it's much better than Ackermann and so on. And in particular, it allows for use of SMT solvers for these kind of problems, at least for the C-VASS case, continuous VASS case. So a natural question was, if you add a stack, how much more does this problem get? How much more difficult does this problem get? And our theorem shows that reachability for continuous PVASS is non-deterministic exponential time complete. So the result is very robust. In particular, the lower bound already holds for a model which can do exact counting up to an exponential number, along with continuous counters. So this was, let's say, against the grain. I think for a long time we were hopeful that this problem would be in polynomial space for reasons that I will not get into. So I will now go into a brief overview of the lower bound and possibly skip the upper bound entirely. And again, the reason I want to go into the lower bound is because I feel that this was the somewhat more surprising result for us. Okay, so here is the chain of reductions that we use. So there is a bounded version of the post correspondence problem. So PCP is well known to be undecidable. The bounded version, there's a bounded version which is known to be an X prime hard. And so we start from there and then we proceed through a chain of reductions. So we go over to, so this is a very descriptively written model, but it looks a little bit scary. I'll tell you. Okay. I have 2 minutes left. Okay, so then maybe maybe I should choose to show you one part of this. Yeah, okay. So let's say that the first step is not really very difficult. So let's just look at this model, which is the 2. So it's a 2CM RL.2 plus 1 is a 2-counter machine with, so the RL stands for run length bound for the reachability. And you can multiply by 2 and you can add by 1. And the problem we consider is equal reachability. So you can sort of think of, in PCP you have 2 strings which need to be the same. So that's how you end up getting equal reachability for this model. So this other model is very close to continuous VASS. So here you have 0 testing. You still have a run length bound. And all things are constrained to be, all counters are constrained to be in 0, 1, right? So, so the goal is to simulate this 2 counter machine with dot multiplied by 2 plus 1 using one of these machines. And so here you note that the largest counter value attainable is 2 to the m. So you can represent, the idea is to represent a number occurring in our 2 counter machine m as n by 2 to the m as this fraction. And we solve the goal, I mean, we have these 2 challenges. First is we have to somehow create this exponentially small number, which is like 1 by 2 to the m inside a continuous counter. And we also have to simulate addition and doubling. So roughly speaking, the main idea is somehow using the 0 tests, you can control the firing fraction, right? So this fraction, you can force it to be 1 by using 0 tests. So, and then the second part of it, which is moving over from this restricted sort of 0, 1 fractions to PVASS, uses this idea of using exact counting in order to simulate multiple 0 tests. So in particular, the crucial thing here is that we can in fact show hardness for just the PVASS model with a run length bound which is in binary. So all we do with the stack is just count, that's it. And so this means that so this basically means that even if you have, for example, a Boolean global state, right? So then you can count up to an exponential number inside this with a bunch of Booleans in the global state. So already for a model like that, you would have this lower bound. Okay, so with that, I skip the upper bound as well. So to conclude, we showed that reachability, and in fact, we can show that even coverability for PVASS is non-deterministic exponential time complete. It would be interesting to add continuous counters to more powerful models, such as higher order Pushdown automata, and see whether we can get decidability results. It is, I think, equally interesting to study more restricted models in the context of continuous approximation and see if we can get better complexity, hopefully like in p-space or NP, so that we could actually put it to use. Yeah. Okay, thank you.
Questions?
So you started off with the analogy of asynchronous programs with VASS, and then what would CVASS correspond to in a programming language setting?
Yeah, where you have like just one thread. So you can think of it as yeah, you just have one thread which is allowed to do recursive calls.
But this fractional firing?
So the fractional firing, as I mentioned, there are 2 parts to it, right? So one is where you have the VASS model and then you add one stack to it. So this is Pushdown VASS. And then the continuous part of it is this sort of over approximation where you are allowed to fire the count, whatever you do on the counters, you're allowed to fire that fractionally. So now you have sort of rational values on the counters, but the stack operations are still discrete. Because it doesn't make sense to say I push half an A, or at least we couldn't think of what that would
So mapping it back to asynchronous programs, there's no direct mapping except for this approximation thing that you said.
Yes, I would say so. Yeah.
I see.
So there are with just the CVASS without the pushdown, people have used it, have implemented this, and it actually does quite well. I mean, yeah, practically speaking, it does quite well as compared.
Can I ask one more question?
So a long time back, Rupak and Ranjit had this result that you could do some kind of under approximation, over approximation with bounded counters, and with a small bound, you can detect that you have actually finished, and you can actually say that nothing else is reachable. I don't know if you know this kind of result, but it made this whole thing, possibly practical because you could implement that algorithm. Are such bounded counters and detection known for such problems as well? And have you looked at that?
No. So if you bound, so there is no continuous aspect to this. This is just a bounded counter. So it's just like a global state and bounded counters. So yeah, I mean, so then in essence, this is somehow a succinct version of a finite state machine, right? Because
no. It's the original problem, except so in general, there is a very large bound, such that if you search up to that bound, it's okay. But in practice, so it could be much less, and you can detect if it's much less. It can be 2 or 3 even.
I see.
And then you detect it, and they showed that for some practical systems it was possible.
So I'm not sure how this would how this corresponds to the original model, because so the continuity in the larger scheme of things, it's nice. But with this run length bounding, one of the things that you see is if you take the same run length bound and you just directly apply it for a VASS without the continuity, then you can keep track of everything in P space.
Well, this is exploiting the instance complexity rather than the burst case complexity.
Okay.
So.
Right. So you just mean in terms of implementations, whether you can look at, yeah, okay, thank you.
Any other questions?
I was just wondering whether you think this kind of continuous approximation approach, whether you'd be able to get results to hold in the setting of, well, I'm not sure if they exist, but branching pushdown vector addition systems, where you have the kind of branching construct.
Yeah, I think there is, yeah, I think there is a likelihood that there is some very general decidability result which is there in this for this particular model. So we are looking at it, and I mean it would be interesting. At this point, we are positive that something would come out of it, but regarding complexity, it's quite unclear how bad these things would be. Yeah.
So, okay, are there any questions?
No, go ahead.
Okay. These executions with the fractional firings can also suffer from, I guess, xenoness.
Sorry, what is xenoness?
Where you keep decreasing only by half.
Yes, in fact, so okay, so that is part of the reason why certain things work well. In fact, so what you can do is, if you're interested in, for example, just reaching some particular global state, there are some ways in which you can sort of drop the fraction by half at each step, and then you can sort of saturate certain sets of counters that you want, and then you can go somewhere, you can desaturate. There are certain things, interesting things that you can do. So that's part of the reason why certain things are easier.
So if I restrict my model to be only only non-Zeno runs, then this complexity would be hard to get.
So by that, do you mean that you want to restrict the numbers to be, let's say, sub-exponential in some sense?
I mean, that's one way to say, but I could just say the semantics of my CVASS is that all runs are non-Zeno. And then under this model, the reachability would
possibly. So this is not clear. I mean, what would happen? This is not clear. Yeah.
Okay.
Yeah. So yeah. So especially the upper bound, which I didn't go into, it uses a lot of the previous technology from Blondin and Hasse, who studied the case without the stack. And there it's so the main content of the upper bound over there is a lemma where they show that every run is characterized by 3 different runs, where you just go from one place to somewhere, and then over here you are allowed to go below 0 in the middle run. Then here you are again. So there is a certain way of, and it's important for that particular characterization that you are able to somehow pump runs by repeating it, making small fractions and repeating it multiple times. So it would be interesting to see, if you disallowed those kinds of behaviors, then what would happen?
Thank you.
All right, let's thank Ram again, and that's the end of the session.